Hello everyone. Today we'll continue our discussion on probability distributions and distribution functions. We are going to introduce some new terms. Of course, many of these terms we have already used in basic probability distributions, but we will study them in a more rigorous way here. So, one such term is point of discontinuity. Okay, point of discontinuity. Now we know that distribution functions are right continuous. They need not be continuous from left. As a result, we know that for discrete distributions, you may get something like a step function as distribution function. So as soon as you have a step function, you know that there is a discontinuity at this point, say this point, right? Because from left the value is here, from right the limit is here. So there is a discontinuity. So basically these points would be called as points of discontinuity. So what does it mean? Points of discontinuity are those points for which there is a discontinuity. So limit from left, so limit x going to x naught from left, so x going to x naught minus of fx is not same as limit x going to x naught from plus side of fx. Okay, so the left hand limit and the right hand limit are not equal. In fact, we know that since the distributions are right continuous, this is same as saying that limit is not equal to fx. This left limit is not equal to fx. So limit x going to x naught from left is not equal to f at x naught. Right limit is equal to f at x naught because they are right continuous, but left limit is not equal. Okay, so these points are known as points of discontinuity. So in every discrete distribution, wherever you see a step, that becomes a point of discontinuity. Okay, now we will see one interesting result about point of discontinuity. Let me state the result. Let script D be set of points of discontinuity for some distribution function f, for some distribution function f okay, then the result says D can be at most countable. Okay, not can be, actually D will be at most countable. D cannot be uncountable. Okay, so let us try to prove this result. The proof is quite interesting, so let us try to prove. So let Dn, now I am not writing script D, let Dn be set of those points at which size of discontinuity is larger than or equal to 1 by n. Now of course you might be thinking, what is meant by size of discontinuity? So size of discontinuity is nothing but the jump size or step size. Okay, so right, so the difference between right limit and left limit would be the size of discontinuity. So for example, if you have Bernoulli random variable, you have 0 and 1, so you have jumps at 0 and 1. So jump at 0 is of the size 1 minus p, because PMF at 0 is 1 minus p and PMF at 1 is p. So jump at p is of the size, jump at 1 is of the size p. So size of discontinuity for this point is p. Size of discontinuity for this point is 1 minus p. Okay. Now, so let Dn be the sets of points for which size of discontinuity is larger than or equal to 1 by n. So of course D1 would be set of all those points for which size of discontinuity is 1. So if you can think, D1 would be non-empty only for degenerate distribution, because you will have a jump of size 1 at exactly 1 point. So that point would be in D1. But for all the non-degenerate distributions, D1 is going to be empty. Okay. Now D2 would be collection of those points for which size of discontinuity or PMF, probability mass function at that point, is larger than or equal to half. Okay. Now how many points can D2 have? Let me say D2 has 3 points. Let me call them x1, x2, x3. What does it mean? It means probability of x1 is greater than or equal to half because it is in D2. Similarly, probability of x2 is greater than or equal to half, and probability of x3 is also greater than or equal to half. And these are single points. So probability of entire set D2 would become greater than 1 because it would actually be greater than or equal to 3 times half. So greater than or equal to half 3 by 2. So it would be strictly greater than 1, which is not possible. You cannot have probability greater than 1. So D2 can have at most 2 points. Okay. By the same logic, in general, if you have Dn, then Dn can have at most n points. Okay. Dn can have at most n points, because if suppose it has n plus k point, if suppose it has n plus k points, then probability of Dn would become greater than or equal to, each probability is greater than or equal to 1 by n. So 1 by n times n plus k, which is strictly greater than 1. Okay, n plus k by n is strictly greater than 1 as long as k is greater than 0. Okay, so Dn can have at most n points. Okay, and every point of discontinuity is going to be in at least one of the Dn's. Am I right? Why? See, something is a point of discontinuity. So let y be a point of discontinuity. Y is a point of discontinuity means there is a jump at y, so there is a mass at y. So probability of y is strictly greater than 0. And we know, because the sequence 1 by n converges to 0, anything strictly greater than 0 will have to be greater than at least 1 by n. Or you can say even by Archimedean property in your real analysis. Okay. There exists some n naught such that probability y is greater than 1 by n naught. Okay. Why? If that doesn't happen, then we will get that probability of y is less than 1 by n for every n. Okay. So that would mean 1 by probability of y is greater than n for every n, which would mean that all the n's are less than 1 by probability of y, which would mean that 1 by probability of y is an upper bound for set of natural numbers, which is impossible because set of natural numbers are unbounded. Set of natural numbers is unbounded. Okay. So there exists at least one n naught such that probability of y is greater than 1 by n naught. Therefore, y would belong to dn naught for at least one n naught. In fact, it would belong to n naught plus 1, dn naught plus 1, dn naught plus 2, etc. also. Because if once the probability is greater than 1 by n naught, it is greater than 1 by n for every n greater than n naught. Okay. So since every discontinuity point is in at least one dn, script d, set of all discontinuity points, is union of dn's over all n's. Okay, you can write dn greater than or equal to 1. Okay, and we also saw that every dn has at most n points. Therefore, every dn is finite. It cannot have more than n points. D1 has 1 point, D2 has at most 2 points, D3 has at most 3 points, and so on. So every Dn is finite. So script D becomes countable union of finite sets. Okay, script D becomes countable union of finite sets. Therefore, script D is at most countable. Okay, script D is at most countable because it is countable union of finite sets. So script D cannot be uncountable. Okay. Similar to script D, I can define script C as set of continuity points of distribution function. Now, every point on R will be either a discontinuity point or a continuity point. So C union D is always R because the distribution function is defined on entire real line. Right, fx is defined for every real line irrespective of support of x, support of f. Okay, x, yeah. So C union D is R and this is at most countable means this will always be uncountable because we know R is uncountable. So if C were also countable, then union of two countable sets would become uncountable, which is not possible. So C has to be always uncountable. So set of continuity points is always uncountable. Okay. Set of countable points and continuity points is those points at which distribution function is continuous. Now let us define one more term, that is point of increase of a distribution function. Now if we have this step type of function, obviously these are points of increase because at these points distribution function is increasing. But on the other hand, if you have a continuous distribution function, something like this, then every point is a point of increase. Okay. So how do we define point of increase? Point of increase is defined as those points for which, so x is a point of increase if f of x plus epsilon minus f of x minus epsilon is greater than 0 for every epsilon positive. Means if you take any point to the right side of x and if you take any point to the left side of x and if the difference between CDF at these 2 points is always 0, means for every pair, in fact you can also have epsilon 1 and epsilon 2. Okay, they don't have to be same epsilons. Okay, you can also have different epsilons, still it works. So as soon as you go to the slight right and as soon as you go to the slight left, there is always a difference, then you say it's a point of increase. So points of discontinuity are definitely points of increase because this gap is always positive, but some points of continuity can also be points of increase. Here these are points of continuity, so these, but they are not points of increase because the distribution function is flat there. Okay, so every point of discontinuity is a point of increase, but every point of increase need not be a point of discontinuity. Okay, so in continuous distribution functions, every point in the support of the random variable would be point of increase. In the discrete distribution functions, again every point in the support would be point of increase. Okay. For a distribution like normal, support is R, hence every point in R will be a point of increase. Okay, so what is the conclusion? Points of increase, set of all points of increase can be either a singleton set or a finite set or a countable set or an uncountable set also. It can be R also. Okay, so even though set of all discontinuity points was always a countable set, at most a countable set, set of points of increase can be uncountable also. Okay. Now, dense set. Do you remember definition of dense set from real analysis? A subset of R is said to be a dense set if set of limit points of that set is entire R. Okay. So, points of continuity, set of points of continuity is always a dense set. Okay, from that you can always extend to entire R. Okay, because it can be uncountable. In fact, it is always uncountable. It is always a dense set. So if you know distribution function values on a dense set, you can extend it uniquely to entire R. Okay, so if values of f are known on any dense set including points of continuity, set of points of continuity, then f can be uniquely determined on entire R. What is the implication of this? If you have two distribution functions whose sets of points of continuity match, means if you have say f1 with c1 as set of continuity points, f2 with c2 as set of continuity points, suppose c1 is same as c2, and if f1 at x is same as f2 at x for every x in c1 c2 are same, so let me call them c, for every x in c, then they match over entire R also. Okay, so f1x and f2x match for every x in R also. Okay, so it is enough to know the value of distribution functions at points of continuity. The values at points of discontinuity can be figured from these very easily. Okay, now we have one more important result in distribution function theory. So that is called as Jordan decomposition theorem. Okay, so Jordan decomposition theorem. So let f be any distribution functions, f be any distribution function, single distribution function, then f can be decomposed into two components as follows. So how we decompose f? We write f as L1 f1 plus L2 f2. Okay, we write f as L1 f1 plus L2 f2, where L1 L2 are greater than or equal to 0, L1 plus L2 equal to 1, f1 is a continuous distribution function, f2 is a discrete distribution function. Okay, so every distribution function can be expressed as a mixture because L1 L2 are positive and they are adding to 1, so it's like 60% of f1 plus 40% of f2, something like that. So every distribution function is a mixture of a continuous component and a discrete component. So when you have a purely discrete distribution like say Bernoulli or Poisson, your L2 would be 1 and L1 would be 0. When you have purely continuous function like say normal, your L1 would be 1, L2 would be 0. Whereas when you have mixture, your L1, L2 would have some positive values. Okay, consider this distribution function and you have seen these type of distribution functions in priority distributions, I am sure. So try to decompose this into discrete and continuous part. How do you do that? You check at every point, every changing point means so you check at this -2, then 0, 5, 6, whether there is a discontinuity, whether there is a jump. For example, at -2 you can clearly see there is a jump of size 1/3. So discontinuity points include -2. At 0 also there is a jump, so 0. Then at 5, if I substitute 5 from this side, it would be 5 minus 5 whole square. So this is 0. So it is half and half. So 5 is not a discontinuity point. And if I substitute 6, then I have 6 minus 5. So 1 square by 2. So half plus half. So it is 1. So left limit and right limit for 6 is 1. So possibly the discontinuity points are only these two, -2 and 0. So you see what is the mass at these points. Find L1, L2 and express this F as a linear combination of two distribution functions. One is one is discrete, having support as possibly -2 and 0, and one is continuous, okay, having support possibly in the range 5 to 6. Okay, so try to do this. Try to compute CDF F1 and F2 and the mixing proportions L1 and L2. This is your homework. Okay, and another homework is construct two one discrete and one continuous distribution function, and then mix them and write down the CDF of the mixture. Okay, so second homework is you don't have to take standard variables. You can take standard distributions like uniform, exponential, etc. and Bernoulli Poisson, but you can also construct on your own. So take one discrete and one continuous CDF. Take P not equal to half. P means mixing proportion. So take L1 not equal to half and of course not equal to 0, and construct the mixture distribution from these two distribution functions. Okay, so for today let me stop here. Thank you.